I just started I think I started the recording. Yes, the recording has started. So we switch to English. Welcome everybody. Good afternoon, and it's a pleasure to welcome in particular our guest today, Richard de Souza. Let me briefly introduce our guest. Richard got his PhD in astronomy in 2016 at LM University in Munich, in Germany, with a thesis on stellar halos of galaxies, supervised by Genevieve Kaufmann. Afterwards, he moved at the University of Michigan in the US for his postdoc until 2019. And then he got a position as a staff astronomer at Specola Vaticana, at Vatican City, since 2019. Richard is also member of the Society of Jesus, and today he will talk about understanding the effects of mergers on Milky Way mass galaxies, linking the galactic accretion history with extra-galactic. Richard, thanks again for accepting our invitation. I'll give you the microphone, and I will tell you 5 minutes before the 45 minutes time.
Lovely. Thank you. So thank you, everybody, for inviting me, for giving this talk. What I would like to do today is to give an overview of the field of the last 5 years, the work which our group has done, and try and explain to you the effects which we think that mergers have on Milky Way mass galaxies within the local volume. So what I will try to, the outline of the talk will be, I will firstly briefly try and remind you of the great advancements we have done in the last few years with Gaia and understanding the accretion history of our own Milky Way and the effects of those mergers. And then I will try and connect this and link this to other galaxies in the local volume. So I will not be talking about one particular paper, but I'll be briefly mentioning a lot of work. So I have to say I will not go into the specifics, but give a very oversight view at 5,000 meters high, a broad overview of the field. Okay. So let's start off with the question which I personally am very interested. We know that galaxies come in many sizes. So I have here pictures of a number of galaxies of various sizes, and each of these columns have about a factor of 100 in their stellar mass. And we know that this sort of growth is due to various number of reasons, due to merging, hierarchical merging, etc. But we also know that at a single mass, at the mass of the Milky Way, we also find a large variety. We find variety of thin disks with galaxies with bulges. We have lenticular galaxies. We have even ellipticals. And the standard paradigm tells us that the galaxy properties are structured by two things: mergers and secular evolution. And in this talk, I would really like to consider the question, what are the effects of mergers on these galaxies? That's the question I like to answer. So to remind you, the way we can understand the merging history of a galaxy is by studying its stellar halo. And the stellar halo is made up of the remnants of past mergers. And because of their long scattering time, the stars in the stellar halo preserve information kinematically and chemically about the galaxies in which they were formed, and therefore they can inform us about the galaxy merger history. This is common knowledge. So in the Milky Way, we have had a great revolution, basically due to two things. We have great revolution due to the advancements of Gaia, and we have a great revolution due to in combination with the various spectroscopic ground-based surveys. And perhaps the biggest thing we have understood, the biggest revolution, is that we have understood that our galaxy experienced a large merger, which has now been dubbed as the Gaia Enceladus sausage. And we have in some ways been able to constrain its mass its metallicity, and its approximate time in which it merged with the galaxy. So we can call the last big major merger of our galaxy. So just very briefly, we found first hints of this in the Gaia data when we try to look at people try to look at stars which around the solar neighborhood, which had kinematics very different from that of the sun, and they found that the CMD split into two particular branches, and they found that the one which is on the left, the more redder based CMD, is that due to a distant merger. A lot of work has been done on this, and both the groups of Amina Helmi and groups of Vasily Belakurov have done tremendous a lot. But I'd like to demonstrate this best by using stars not in the solar neighborhood, but stars which are out there in the halo, because the Milky Way has that particular difficulty that which we observe both in the solar neighborhood, but both outside in the. It's more difficult to observe in the halo, because that's in the halo where we should be actually looking. So the survey which I particularly appreciate and like, and is great work being done, is the H3 survey led by Charlie Conroy. And this particular paper by Rohan Naidu shows very clearly the Gaia Enceladus sausage. It's a long elongated structure in the first plot, which is elongated, really radial. It has a metallicity of about minus 1.2, which is, it also has enriched alpha abundances, and it has little or no rotation, which is seen in the energy and the angular momentum plot. But more than that, because we have so much knowledge about the stars in the Milky Way, we can also identify other structures, and many more other smaller structures have been found. But for now, I would like to concentrate only on the Gaia Enceladus sausage, because that is the biggest thing which hit the Milky Way, and that which you would think that would have caused the largest damage or largest changes within the Milky Way. We have also been able to understand when this galaxy, this Gaia Enceladus sausage, was accreted by looking at the ages of the stars of these galaxies. So we look at the main sequence turn-off stars, the same work, the work led by Anna Bonaca, also of the H3 survey, but many others have also done similar works, including Galat et al., where they have actually shown that the accreted stars have a shutout in star formation about 8 to 10 gigayears ago. And so we can approximately suggest that, yes, this merger happened about 8 to 10 gigayears ago. So we have a mass, a metallicity, and an age. I would also like to say that people have also tried to understand this merger or constrain this merger using other tracers, which are not only the stars in the stellar halo. So the people have tried using this with the globular clusters, with streams, and with satellite galaxies, which have done much more success with the globular clusters using the age-metallicity relationship. And here I'm just trying to show you that we have the streams, we have the satellite galaxies, and people try to look for clustering in their action momentum, or also try to look at age-metallicity relationship of the globular clusters to try and constrain the same mergers. And it's important to note that the stellar halo is telling us one story, and it should be that the other tracers, any other tracer, should also confirm that story and not tell us another story. And this is so in the Milky Way, and this is a really nice advancement. Once we know the merger, we can also say, what did the merger do to our galaxy? So one of the things which people have long known is that the galaxy has had a thick disk, and now we have a better understanding that maybe this thick disk was caused by that merger, the Gaia Enceladus. Vasily Belakurov has called this the Great Splash, and this is seen in the bluer part, the more metal-rich part of the CMD. It has quite like halo kinematics, but is at a much higher metallicity and is co-eval. I mean, at the same time as the stars are the same age as the accreted stars. And this is seen also in Anna Bonaca's work, is in the red part of the age of the star formation rate. You see that there was a large burst in star formation within the disk of the Milky Way. And these stars are much more disturbed, and they are much different from the thin disk that we have. So we know that it caused a great splash within the Milky Way. Now, this is what we know. This is a small reminder of what we know. My question is, can we reproduce or understand the same things for galaxies out there in the local volume? So first, let me try and justify why I'm trying to concentrate on the galaxies in local volume. There are about a dozen or so Milky Way-mass galaxies out in the local volume. And we must admit that from the 1960s onwards, most of our intuition about galaxy formation has been built from these galaxies. Yeah, from M31, from Cen, from NGC 49, from NGC 253, from the Sombrero galaxy. Most of our galaxy intuition has been built from these. Moreover, we have a lot of information out of these galaxies. We have studied their structure in the near infrared with S4G survey. We know so much about the ISM and their star formation. And we know that these galaxies can be studied with in resolved stars, at least their halos, can be studied with HST, with JWST, with the future Roman telescope, and also with large ground-based telescope, 8-meter class telescope. So the local volume gives us enough number of galaxies with large spread in their diversities to understand what will be the different effects of mergers in this galaxy. So we study their stellar halos in resolved stars. I like to call them resolved stars because galactic cirrus is a major problem when we try to study low surface brightness regions of the stellar halo. So it's important that we go to resolved stars. So we can study this in two principal ways, and this has been studied in two principal ways. We can use HST, space-based telescope, and this HST with this narrow field of view, we kind of study pencil-like beams on the halo of the galaxy. And this has been led, the GHOST survey is a very clear example of this sort of way of studying the galaxies. Or the other possibility is to use large ground-based surveys of the halos of these galaxies. People have done this for M31, M81, etc. And the most famous of this example would be the PANDA survey of M31 Galaxy. You really need a 6 to 8 meter class telescope to be able to resolve the stars and the stellar halo. These are the two main ways in which we can study these resolved stars in the local volume. So let me now just summarize in the last 7 years what we have been able to achieve. So this is a plot which is the stellar halo mass metallicity relationship. And here are the number of things I'd like to point out. First of all, there are about 14 points in this plot, including the Milky Way. So today we have studied accurately about 14 Milky Way mass galaxies. Some of them are a bit larger than the Milky Way, some of them are a bit smaller, but these are 14 galaxies which I have studied their stellar halos. We have a mass and we have a metallicity, and I will come to time a bit later. Okay, and this is the latest iteration of this plot, the latest plot, and we can see that the first thing which comes to our mind is that there is a large spread in the halo masses. So think of the x-axis as the halo mass of the galaxy, and the vertical axis as the metallicity. Now the metallicity is measured at 30 kiloparsecs along the minor axis. The reason why we choose a minor axis is that we would like to get stars which are not contaminated by the disk, or what we would like to call pure accreted stars. And you may ask, how do we know the total accreted mass? We do not know the total accreted mass, but we actually try and measure the mass of the stars in the galaxy in an annulus, and then we kind of extrapolate it with models. There is a bit of an uncertainty in the accreted mass, but more or less, I think it is quite accurate given the uncertainties in the mass. So first thing you notice is that galaxies have a big difference in the accretion mass. You have M101, the pinwheel galaxy, which has a stellar halo about the size, a little smaller than the LMC. Sorry, the SMC, the small magnetic cloud. And you could think of, M31, Sen-A, M10, Sombrero galaxies as having accreted something really large. I mean, their stellar halos are humongous, almost half the size of the Milky Way. So there is a large spread in their metallicities, okay, and their masses, which means also that these galaxies probably accreted a diverse amount of have very different accretion histories. Okay, this is the first thing which strikes us. The second thing is a very, quite a tight relationship between the metallicity of the halo and the mass of the halo, and it kind of reflects the metallicity mass relationship of dwarf galaxies or Milky Way-mass galaxy, which I'll also put there. It's a bit offset. And the reason why it's offset is easy to understand. We're not measuring the center of the galaxy. We are measuring it off by 30 kiloparsecs. So think of gradients, which could, decrease the metallicity. But also, we know that the slopes appear to be slightly different from the metallicity mass relationship of normal galaxies. And I will come to it a bit later. But this is summarizing all our knowledge. And this is really, like to point out, a lot of work done by a lot of groups and a lot of people. But it is now summarized in this plot. The second thing which we can also do is be able, I said we need a mass, metallicity, we need an age. We can also get to ages in a few. It's much more work, it's much more difficult. And we kind of do the same trick. We try and get CMDs down to the main sequence turnoff to get ages of these, to get a shutdown in star formation, which would signal the time when the galaxy falls in, gets disrupted, and stops forming stars. In the M31, we have been able to, with a big investment in time, able to get down to the main sequence turnoff of the halo. We're talking about 150 orbits of HST to do that. And that goes about 6 magnitudes, below, 6 or 7 magnitudes below the RGB. So that's a real, very deep CMD. But for galaxies, a bit further away, so this is the M31 is about 1 megaparsec away. But for galaxies much further away, we can't go so deep. So there have been 2 galaxies which have been studied. One is M81 and the Sen-A, both around 3.5 kiloparsecs away. And these galaxies have been studied to the red clump. And you can try and get an age also to the red clump stars. Yeah, it's not that as precise as the main sequence turnoff, but you can get an approximate age. And this has been done by Darrell, Peter Darrell, and Marina Rechkuba, whom most of you probably know. Further away, it becomes even more difficult because these galaxies are much more further away. In a recent work, trying to imitate what also Marina Rechkuba has done for Sen-A, we have been able recently to try and use the AGB stars in the stellar halo to gauge a shutdown in star formation. And what I'm showing you are the CMDs of 3 particular galaxies, NG253, 891, and 3031. These are galaxies at various distances from 4 to about 7 megaparsecs, 7 megaparsecs away. And what we've done is a simple ratio of the number of AGB stars to the number of RGB stars. And we find that our models show that the number of these stars, the ratio of these stars correlates very well with the shutdown in star formation rate, which means that younger populations will have more AGB stars and older population will have much fewer AGB stars. We have also calibrated this with large dwarfs within the local group. And what we have been able to show is that so now we have ages of at least a number of galaxies. We have, of course, Milky Way, M31, Sen-A, but we have 3 more galaxies. And the hope is that we can extend this in the future. But I'd like to point out that this result shows that the stellar halos of large galaxies or large stellar halos have been formed rather recently. So both M31 and Cene are approximately the same ages, whereas galaxies like the Milky Way, M81, which are much smaller, have much older ages. This is a result both found in observations, but now but also found in the models. So this is the basically understanding of how we get the mass, metallicity, and age. Let me move quickly forward. To interpret all this data, we need models, definitely. And the models have been around and have got better with newer data. So most of the models, I like to summarize, these models have been summarized in a number of papers out over the course of the decent papers led by me, also the Auriga simulations by Antonella Monachesi. And basically you can understand most of the models based on the stellar mass halo mass relationship. Now, the Milky Way mass galaxies sit at the knee of the stellar mass halo mass relationship, and the stellar mass halo mass relationship becomes rather steep below the Milky Way. So based on this fact, you can basically understand three major principles to explain our observations. So the first thing is that on the extremely left is that the mass of the largest progenitor can be constrained from the mass of the stellar halo. So if you have basically using your models, you can take your accreted mass or your stellar halo mass, what you measure, and you can automatically nearly predict what is the mass of the largest thing which fell into the galaxy. And we would like to call it the dominant progenitor from now on. And the reason why most of it is contributed, so I'll come to this a bit later. So the second result, which you can say is that, which I've kind of showed earlier, is that there is a kind of like a correlation between the mass of the largest stellar halo and the time it was formed, or time of accretion, or time of merger. And there's this correlation because smaller halos formed much earlier, and galaxies with larger halo, the halos formed much later. They suffered later mergers. As you see in the middle plot, sort of like a broad correlation with a lot of scatter, but there is this correlation. And the third thing is that the third result is basically is that it's kind of showing you two things. So on the x-axis we have the mass of the stellar halo again, and on the y-axis we have a frac dom, which basically means how much of the stellar halo was built by the dominant progenitor. And we see that this ratio becomes closer to 1 very quickly when you have a large stellar halo. So anything which has a large stellar halo is built from most of its mass is built from one large progenitor. And all this boils down to the steepness of the stellar mass halo mass relationship. So it basically, what it's trying to tell you is that there are not so many small galaxies to merge to build a large stellar halo. You really need a big galaxy. So it basically boils down to the stellar mass function, to the stellar mass halo mass relationship, and the steepness of that relationship. Big halos are built by one large project. That's the basic idea which comes out of the models. The models also are quite successful in predicting other things in the data. And what I'm trying to show you is, for a long time, people fussed about the profiles and the metallicity gradients of the stellar halo. So I'm showing you two very different cases. NGC 253 on the top plot from the GO survey has a very flat metallicity gradient. And the M31, which is from the SPLASH survey, has a very steep metallicity gradient. And people fussed about it and wondered about it. And today we can explain all of this by the models. And basically it tells you is that if you have a small stellar halo, you basically are built by a number of galaxies, and you generally tend to have a flat metallicity gradient. if you are dominated by you have a large stellar halo, you're dominated by a larger galaxy which has a metallicity gradient. As the galaxy is merging, it strips, and this stripping also creates the metallicity gradient of the metallicity gradient halo, transferring the metallicity gradient of the progenitor to the metallicity gradient of the stellar halo. And we have seen this in the models. It's kind of, I won't explain these plots, but I will say that, it's seen very clearly in the Illustris and the TNG simulations. It's seen very clearly in the Auriga simulations. Yeah, I will try and move ahead. So let's try and, so the first galaxy I like to talk about is the M31 galaxy. It's the galaxy easiest to decipher in a certain sense because of the wealth of information about the stellar halo, which has been done by a number of groups and people. It's a clear, so we can actually decipher its most dominant progenitor because of the wealth of this work, years and years of work, painful work done by a number of people. Think of a result built on the shoulders of giants, right? So, so the first thing which from the models we see, which is a work which I led a couple of years ago now, it's a bit old, is the large. So M31 is distinguished in having a very large stellar halo. Its stellar halo is about 10.3 in stellar mass, so log 10.3, which is about half the mass of the Milky Way. And what is quite obvious is that from the models, very clear, using various models, it's very clear that if you have a large mass, then you probably have accreted a large progenitor. You have accreted a large progenitor, and you have accreted a progenitor greater than a certain mass, greater than 10.3. And this progenitor must have been accreted in the last 5 gigayears, okay? And must have a metallicity also of about 0.1. So that's very clear from the models. What you can do is even more better. You can try and also 5 gigayears is a long time. So you can actually, because of the wealth of the star formation histories of various objects in the stellar halo of M31, external to M31, you can have the star formation history. You can look at the shutdown in the star formation history of these objects. And in most of these objects, you see that around 2 gigayears ago, approximately, there has been an extreme shutdown in star formation. And you can therefore use this fact to say that, this didn't happen 5 gigayears ago, but the galaxy merged with M31 about 2 billion years ago. And because of that metallicity gradient, you can almost say that the core of that object, the remnant of that object, should be the enemitous object M32. The remnant should be M32. This is the result we suggested in 2018. It's a view which is slowly being favored by the astronomers. So there are some doubts about whether M32 is really the remnant of the object. But by now, everyone agrees that M31 accreted a very large object, half the mass of the Milky Way about 2 gigayears ago. What is the remnant is another question. But this is very clearly seen in the model. So you can have dynamic models done by me, but also dynamic models by other people, Francois Hammer et al., where you can see how the galaxy is being accreted onto the M31. There's a burst of star formation in its center, and that star formation extinguishes and forms all the tidal features which you kind of see, with the various star formation histories which you see in the model and the data also. So I would like to propose that M31 merged with a large progenitor, half the size of the Milky Way 2 gigayears ago. The remnant of that progenitor is M32. So the progenitor, we would call it M32P for progenitor. And the mass of that galaxy would be half the mass of the Milky Way. Mind you, that's a rather large galaxy. That would have been the third largest member of the local group after M31 Milky Way. And then you would have M32P. Then you would have M33, the LMC, the SMC, etc., etc. So a pretty large galaxy. But what we did in that paper also was to say, okay, if we think this is M32P, that we called it, and M32 is the remnant. M32 is a strange object. It's a very strange. It's a very compact galaxy, as most of you will know. It's a very compact galaxy. It's very dense. It has a very high metallicity, much higher than its stellar mass. And Sandy Faber, the famous Sandy Faber, she had predicted right in the 70s that M32 would be a stripped galaxy based on its high metallicity. And now we kind of understand also that, where did the rest of the mass of M32 go if it was stripped and became like that? And the rest of its mass is in the stellar halo of M31. I like to think of it as a peach, with a fruit with a very hard seed. And as the galaxy is falling in, it gets tidally disrupted. But what finally remains is a very compact, the center, which resists tidal disruption. If you want to look around in the local, universe, you can ask galaxies, what do we have galaxies as mass of 10 or half the mass of the Milky Way and have central densities as comparable as that as M32? And you get a number of objects, 8 of them, out to 24 megaparsecs. And some of them are, galaxies which many of us know and love. So we have here M82, 2 of them are within 10 megaparsecs. M82 is there in GT034. You also have the M51B, which is merging with M51A. It's quite interesting to see how you can produce these galaxies with such high densities in our models. Okay. We also know, due to work of a number of people, what are the consequences of that merger on M31. We now know that there was an extreme global burst of star formation in the disk of M31. And this is about 2 gigayears ago. That is, the disk reacts just like the Milky Way reacted to Gaia and Sirius. This is a famous result by the FAT survey, led by Ben Williams. We also know that the disk of M31 was heated up. This is a result of the dispersion in the stars, of the individual stars in M31, as a function of age. And then, as you can see, they have a very high dispersion. It's a very thick disk. The younger stars are very thin. That forms a thin disk. But the older stars, about 5 gigayears ago, before the collision, have all been heated up to a high degree. And you can see also it has a much higher age velocity dispersion relation than the Milky Way. So it probably suffered a much larger collision than the Milky Way did. And this is a clear example of a thickening of the M31 disk. Very similar to what happened in the Milky Way, but much more dramatic effect and much more recent in time. Okay. Let's go on to the next closest galaxy which we have. We have M81 interacting with M82 and NG37. The stellar halo of this galaxy is much smaller. It has been studied by the GHOST survey by Antonella Monachesi, by Okamoto in wide field surveys. And recently, Adam Messina, member of our group, studied the stellar halo of this object using ground-based wide field using the Subaru telescope, which is an optimal instrument. And basically, we did this in 3 bands because we would like to do a very sophisticated, and let's put it this way, at those faint magnitudes, galaxy star separation becomes a big problem. And what we are using here is an old trick in the trade is we're using 3 bands and using the locus in the color plot to identify the point sources, the the stars and try to differ them from the galaxies. So we have been able to image the halo of M81. And here you see a stellar halo map of M81, M82, and M45. And what is quite evident over here, where Adam has plotted, you see the stellar halo map. It's a very anemic halo. But you can also see that the halo, the two galaxies are being disrupted, because the circles are the tidal radii, which are calculated using a simple model. And you can see these galaxies are being disrupted, and eventually would contribute to the halo of M81. Now, Adam's Messina is bold. So he hazarded a picture trying to put in our work on M31 and M81 together. So right here I have the halo, so the metallicity mass relationship, which we've seen before. This is a few years earlier with less number of plots onto the rear. So you can see where M31 is, you can see where the M81 halo is right now. So it's a little larger than, it's comparable to the Milky Way, and is also comparable to the metallicity of the blue plot. So now he said, okay, let's try and count all that unbound stuff which is around M81 and 3055. Let's try and count that up and add it to the stellar halo. What would be its metallicity? What is mass? And you move to the green point. So the stellar halo is growing. I mean, in the future, that will become part of the stellar halo. But eventually, you can hazard a guess that both the two galaxies would be completely destroyed. And all of their mass would end up in the halo of M81. And basically, M81 then would move up the plot into the red point over there. Basically, consider the metallicity of the two large objects, especially M82, and consider all its mass with M82 and M37. You would have the mass and the metallicity of it. It's a bit uncertain, of course, with the mass and the metallicity. You will have gradients and things like that. But basically, you would move up that relationship. That's exciting. This is because he has the guess. And based on our previous work, therefore, the kind of idea which comes into play is this. This is something which we suggested already in our 2018 work. So on the right-hand side, you have M31 and M32, right? So that's the end result, what you know after 2 gigayears after the merger fully happens. But we also had this idea of searching for M32P analogs. And the two analogs which I mentioned, one was M51B, and we had M82. And both of them are undergoing mergers, but in different stages. So you can actually try and put together a timeline of what would happen, what happened in the past, or try to build our intuition, right? We're trying to build our intuition. What happened in the past? What will happen to M81 in the future, M51? So basically, the first thing which you notice, which I think will point out to you, is that M82 experiences a burst in star formation, as it approaches. That is the thing which we know. Then it gets disrupted. You also have the disk of M51 lighting up, just like M31 lit up a couple of years ago. And basically the end result would be the M31 and M32. Let me quickly go ahead fast because I'm running out of time. So M94, we also studied its stellar halo. It has the largest pseudo bulge in the local universe. And recently, Katya Gottsman submitted this papers under revision. We studied its stellar halo, kind of again with Subaru. We kind of see an extensive blue. You see an extensive, much redder. Sorry, you see a much redder, more metal rich, concentrated towards the galaxy. I mean, you have a much metal poor stellar halo, much more dispersed. So one is clearly the disk, and the other side is a real stellar halo. So it's a dual population. And you can actually work out what will be the profiles of these two things. And what we have found is basically that M94 has a very small stellar halo. But this brings the question, do mergers correlate with bulge masses? So M94 has one of the largest pseudobulges in the local universe. And with such a small stellar halo, which has such a small merger, definitely could not have caused the pseudobulge of M94. But more than that, we can also do a kind of, we have all these bulge masses. Some are classical bulges, some are pseudobulges. And we have all these halo masses, which are a proxy now for the largest merger which comes in. And we find that there is absolutely no correlation between the bulge mass and the halo mass or the most dominant progenitor, which means that the most dominant progenitor is basically not the cause of the bulge and not the reason of the bulge. This is a result which has come out of this work. What we have noticed and what we have been studying is this, is we think mergers not only cause star formation, heat up the disk, but also bring in large number of satellites. We know this from the LMC. LMC is bringing in a whole bunch of satellites into the Milky Way. And if you look at these large wide field studies of the halo of both NGC 5128 and M31, you immediately notice two things here, large number of streams. Both of them are large halos, and you see a large number of streams. And I want to point out to you that apart from the very large giant stellar stream, the smaller streams, if you see a stream at that kind of surface brightness, you know that this stream is about the size of a Sagittarius-like object. Okay, so that's the thing which you need to keep in mind. So if you see a stream, the size of it would be a Sagittarius spiral. Both of them have had recent mergers. Both of them have had large stellar halos. And from this, we kind of did a small study and tried to understand what are the satellites which come in with large mergers. And what we realized is that if in an accreted galaxy, which is something like M32P in a simulation, the number of satellites which this large progenitor brings, this large merger brings, increases. So if you look at the number of satellites which are surviving today in the lower part of the plot, most of them were accreted along with the merger. You can see this kind of peak along the merger 7 gigayears. This is in a simulation. And what we have actually seen is that we now know that, does this work within the data? So we have today the star formation shutdown times of M31 and the Milky Way. This is a work led by Dan Weiss, where he looks at the star formation histories of all the Milky Way and M31 dwarfs. And he finds that, their kind of star formation histories are very different. Okay, let's consider on T90, which is the time just before shutdown. And if you take the M31 and the Milky Way data, and you try and smoothen it and try and do a profile of that thing, you will see that the M31 data is all lumped together around 6 gigayears, 5-6 gigayears ago. While the Milky Way data, the star formation shutdown time of the Milky Way satellites, is clumped around in two measures. One is rather recently, about 2 gigayears ago, and the other one is about 10 gigayears ago. And you can almost correlate this with the major mergers of our galaxy. For M31, it's this large progenitor, which merged 2 gigayears ago, but which fell in about 5 gigayears ago, bringing in a large number of satellites, entering the radial radius. And for the Milky Way, you have a clear something big coming in with Gaia and Enceladus and associated groups, and something coming in with the LMC. And the data is consistent. I mean, it's very difficult to say which is coming with which, but we can see that large mergers bring in a large number of satellite galaxies. I want to point out that mergers also cause the destruction of satellite galaxies. This is also important because if you look at the number of satellites here in subhalo as a function of time, with the merger, the number goes up, but then immediately it drops. And the reason it drops, one of the main reasons is the number of these satellites also start getting disrupted. There's a, you're moving orbits around, and there's a dramatic change in the potential of the galaxy. So you have a large number of disruption in the galaxies. And one of the results we came about was that if you can almost build the intuition by saying, thinking of the M31 and Sen-A, if you have a large galaxy, and if you see a large number of streams of these Sagittarius-like objects, which are being disrupted, or which are disrupted, then you can almost say that the galaxy has recently accreted a large merger. It's almost like giving you a time frame of large merger. We find a very clear correlation between the number of Yes.
Just to tell you that you have 5 minutes, right?
Okay, I will wind up very quickly. We have find that if you try and correlate the number of satellites and the number of the dominant and the mass of the dominant merger, we have a clear correlation. This is with the data which we have existing. We are still trying to increase the data, but we know the satellite numbers of these galaxies up to MB is 9, so a little bigger than Phonax, Phonax and bigger, we have the dominant, and we see a clear correlation. What this actually means, it tells us probably that satellite mergers are bringing in satellites, but we're still trying to figure out what this exactly means. I'm going to skip this, and I want to talk about one last thing, is that recently it has been rather popular to do the back integration of orbits of the Milky Way because of the excellent, distances and proper motions of the satellites. So people have tried to take a potential, they have tried to simulate the LMC, and they have tried to do a back integration of these orbits. So this is a work led by Ekta Patel, which I think many of you may have seen. So back integrating which orbits, which galaxies came with LMC, which came up. But at the same time, we have also know, and this is a recent thing, is that as the LMC is falling in, it's causing a great change in our potential of the Milky Way. It's causing a wake within the Milky Way because of this, the deformation in the potential. So very dynamic. It's no longer a static Milky Way potential, but a dynamic Milky Way potential. One of the things which we did was we tried to see whether we can actually back integrate the orbits of galaxies using mergers, using simulations. And we find that we're actually doing quite badly. If we try and back integrate the orbits of satellites, trying to imitate an LMC Milky Way pair by just doing a simple thing of two NFW profiles falling into each other, this gives us very bad. And we actually mispredict the orbits of many of these satellites. So the error is basically because we do not have a clear understanding of the changing dynamic potential of the infall of the LMC. So we should treat orbits with a pinch of salt for now. As our models get better, we'll probably do much better than this. But I'll also point out that we know that there is a clustering in, there has long been thought that the energy, the binding energy of the satellites correlates with accretion time. And therefore, you can actually be able to tell you when the galaxy fell in, the satellite fell in from its binding energy. But we found that with the LMC, so think of a large merger, with the LMC, or with the Gaia and this, or M32P for M31, there's actually a scattering in the binding energies of satellites falling in with that particular progenitor. So it's not a very clear thing. And this becomes a problem if you try then to take all these globular clusters, streams, and satellites and do clustering algorithms to try and find what is the progenitor, with whom did they come back with. It's quite popular these days. And we realize that with this scattering in binding energy, even scattering in action space, it's very difficult to do this. This is a work which was led by Khyati Malhan, which attempts to do this clustering in action space. I myself was a co-author on this paper, But later on, we have realized, and as shown by a number of people, a recent paper by Pangini et al., is that the globular clusters, say from progenitor A and globular clusters from progenitor B, are scattered all over the place, and there is an overlap in action and energy space. In some of my own work, which I have done on the right-hand side, I've tried to show is that 3 different progenitors in 3 different colors, and they all overlap in energy and angular momentum, in all sorts of the action space. It's very difficult to separate things out. And perhaps much more work and much more thought needs to be done in how do we go now from the other tracers, globular clusters, streams, and satellites, back to the main progenitor. A word of caution of how we should even look back at the Milky Way. So with this, I like to end, and what I've done is really summarize the field. So I apologize if I've not gone into detail. I'd be happy to ask questions. The first thing is that I can say is that we know the last merger of the Milky Way and we know its effects, thanks to Gaia and the spectroscopic service. And now we are in the process of extending this knowledge to other Milky Way mass galaxies in the local volume. Some of them which I showed you, M31, M81, M64, a number of them which I have not showed you. But we are beginning to see these mergers, understand they are mergers, and also see the effects in this galaxy. And basically, we think now that the merger contributes to the heating of the galactic disk, a burst in star formation, accretion of smaller satellite galaxies, but does not contribute substantially to the building of the central bulges. Finally, one must be a little careful about trying and back it of the other tracers, satellites, streams, global clusters. Back integrating them is a bit difficult because of the dynamic potential. But moreover, anything which falls in with a large progenitor, there is a scattering in the binding energies and the action space. And that we need to understand that better to be able to use these tracers to be able to identify other progenitors. And with this, I stop. Thank you.
Thank you, Richard. Let me stop the recording.